Hello, thank you for attending my presentation. My name is Isaac Vargas, and I'm here to present you virtual testing of in-vehicle data visualization for a CAV. So I come from PTV Group, and we do traffic simulation software. So all the visualizations that I'm going to present you is from the perspective from traffic simulation software. So I thought that it would be very good if I start actually saying what is a traffic simulation software. Hope it's, there you go. So we understand traffic simulation software in two big approaches. The macroscopic side, where we create digital twins of cities, countries, or even bigger areas like the whole European Union, including UK. We have it for use cases such as planning changes in infrastructure. So for example, if you want to build a new bridge or a new pedestrian area and you want to measure the performance of the mobility of people around those areas, then the macroscopic simulation, that's the way to go. Also modifying public transit or including even new mobility solutions like e-scooters. Those are meant to be evaluated through a macroscopic simulation. Traffic here is modeled as a flow, whereas on the microscopic side, all the individual entities or agents are simulated independently. So each individual entity can be, for example, a car, a bus, a tram, a bicycle, motorcycle, or even pedestrians. What these entities or agents have are driving behaviors and movement models. So driving behavior is the characterization of each entity has a perception, perceives its environment, and then reacts to the perceived environment, and then comes to a conclusion of how the next movement should be. And then the movement model, it's characterized based on the type of agent it can be. So a car would move different than a pedestrian, obviously. So the movement model is for that. Then there's the interaction between actors and control systems that could be explicit or implicit. Implicit just like traffic rules, or explicit as traffic lights. So since we have characterized driving behaviors from vehicles that are humanly driven, we have spent already quite the last couple of years integrating our software in European Union projects where we characterize the driving behaviors of autonomous vehicles as well. So we integrate those behaviors into our system. So, but we found out from the common public that there's still a lot of concerns about autonomous vehicles. The reasons behind it is that people wouldn't feel safe from them. They don't want the car to make mistakes, or simply they don't know enough about AVs. So we think that a key part for attacking these concerns of the people is visualization. So we identified a couple of challenges that are behind in different levels. The first of all is that if we want to build a visualization system, sometimes the development of integrating these visualization systems into vehicles could be quite expensive and with a lot of effort. On another level, we don't know about the vehicle's next movement, so there's an uncertainty behind it. And finally, we know that visualization designs must comply with realistic traffic scenarios and situations. So the solutions, we believe in the power of virtual reality and augmented reality to live the scenarios that we're creating virtually for the uncertainty that we are having as a challenge, we think that giving information to the user, being a driver or passenger, is essential. We should be giving the information of the intended vehicle's actions in the near future. And our visualization designs, we think that they should be tested in very different scenarios and evaluate the different visualizations options that apply to one or the other scenario. So there you go. So what is our approach? We want to facilitate the process of creating a VR, AR traffic simulation. So how we do it is that, or how we thought about it, is that we actually broke the process, the problem in two. So we started two developments simultaneously. We have seen that in the industry there is actually no such a streamlined process that could connect a microscopic traffic simulation that could add up some visualization enhancements and then provide the model in augmented reality. So our first task was to create that streamlined process. On the other side, we want to, for in-vehicle visualization, we want to actually take part of one of the vehicles, so you could actually interact with the model itself. So the second task was to extend our co-simulation API. So just to give an example of a result from our streamline process, probably some of you have experienced these situations. There are client meetings, public meetings, or exhibits or trade shows where you want to present the results of your traffic model and your layout of the street design. And you want, typically what happens is that you present the traffic simulation in a video or in a small movie, perhaps. And then what happens is afterwards, a conversation starts around a simple piece of paper. So we believe that there's, like in the fourth picture, we believe that there's kind of a disconnection already over there between what the results of the traffic simulation was giving to the layout of the street. So what we ended up having was creating this streamlined process that we connect our desktop application, which is the one that's having the traffic model. So it's where you describe all your network, the streets, the vehicles, the pedestrian signal heads, and includes scenarios. And the effort was to migrate all the important data into our cloud platform, such in a way that in the end we can stream the animation into any type of AR-enabled device. That could be a smartphone, a tablet, a HoloLens. And really the geniality of what we accomplished on doing that is on the animation, the Web API export animation file. Typically, an animation of such, including a 15-minute simulation, typically would have taken us around ½ gigabyte to have all the vehicles integrated with all the 3D objects and such. So we were able to break down all the 3D objects and the movement of the vehicles. So the animation can be transported in just a couple of megabytes. That means that enables us to provide the solution in portable devices. On the cloud application is where all the magic happens, where we integrate all the systems together, so the scenarios and movements of vehicles from the desktop application, and we integrate also the georeference data, just like such as 3D buildings from third-party providers. That in this example is Mapbox, but also could be, for example, OSM data. So the result of this is that in a simple piece of paper, just like that, we were able to bring the 3D objects because they're georeferenced. And in the end, we tested out some visualization designs so it can be as easy as possible to allow communication to work for communicating your results of the traffic simulation. So in the end, for example, in this case, we decided to go with buildings that are semi-transparent and in a gray. So they are in there to give an idea of how's the layout of the city or this area, but not being distracted, too much distracting for the people. And some of the our main focus was to compare scenarios. And the way we actually thought about it was to include it, hopefully we can see it here. In this video, you can see that on one scenario, you have no connected autonomous vehicles, and in another scenario, you would have the connected autonomous vehicles. So the screen is splitted, and you can simply just swipe around, comparing both scenarios. So we thought that this kind of design for that application would be very intuitive and very easy to compare scenarios just by swiping. And that includes also KPIs from the streets. And for example, this one is using a map that is on the background, but in case that you don't have a map on the background, you can just simply get a QR marker and import a virtual background map, just like what is going to be happening right now, like that. So that allows a lot of portability to offer visualization of your solution. This is actually, you can actually switch off the augmented reality part and make it completely virtual reality, but yeah, we have focused more on the augmented reality part. And here, switching off the 3D buildings, so probably it's also more understandable to see how's the traffic situation. Right? So the next phase was establishing the co-simulation. This is where we use our co-simulation API, and the objective of this is to take part on the simulation. So I've heard in some of the presentations that you can experience your own model and experience your own simulation. So the objective of this is to, yes, experience the traffic simulation, but adding some visualization designs for experiencing what a world of autonomous vehicles would look like. So very similar, we integrate the co-simulation API works in the way that the driving simulator gets data to the traffic simulator, and also the traffic simulator reacts to that data and gives back information. So it's a continuous flow back and forward. So I wanted to present you here the in-vehicle visualization concepts that we tested out and we developed for our driving simulator in this case. So there are 4 in-vehicle visualization concepts. It was a self-routing experience. So imagine the world that you're in your autonomous vehicle, and you would select the route that you are going to take in the next intersection. So for conflict areas such as intersections or roundabouts, probably you would see, or you would select the route just like in the second picture. You would see the map like that. But in reality, if you're being driven by the vehicle, you need to know how it would look like that road and where are you actually going to go. So the first picture is showing that visualization. We implemented communication, vehicular communication, so we would know also the trajectories of other vehicles in conflicting areas, so that the lower picture is showing that type of visualization, the trajectories of other vehicles. Last, we implemented a prediction model which allows us to see 1 to 5 seconds into the future the positions of the other vehicles. So the best design that we could think of so far was for ghost cars, and the ghost cars represent some seconds in the future of the vehicles. And last was the green band, which was allowing communication from infrastructure. So imagine just quickly the case that you're going into a green light, and you don't know if the green light will stay on until you actually pass the intersection. So what we imagine is like following the parameters of the remaining green time and your own speed, there would be a green band in the street that if you're over that green band and you keep moving, then you're safe to go. You will pass on the intersection without any problem. The small video here actually shows how the green band is retracting. So this vehicle is on purpose driving super slow to see how it goes until it's red. And pretty much that's it. Thank you very much for hearing.